to the 51st Elastic Meetup here in Bern in the MIMACOM office. My name is Rocco Schulz. I'm a software engineer here at MIMACOM. And the things that I work with is mainly the Java stack with Spring Boot applications, also lots of work in the front end. And whenever I have time, I try to read up new technologies, new stuff, because I'm curious. So I don't know everything about Elasticsearch yet, but I know that there is a new feature with vector fields, and I found that one really interesting because I saw some potential there. I'm gonna show you what we're gonna do with that. So imagine that you run a web shop that sells paintings, like framed paintings for people who are interested in art. And your customers might be complaining that they have difficulties finding what they are looking for on your e-commerce site because right now they can only browse through lots of categories and tags, and it doesn't really work for them. So what you want to do, you want to provide them with a visual search similar to what Google does with the image search. You might know that you upload an image and then you see similar things. So in the end, your potential customers might just go to a museum or art gallery. They might take a photo of something that they like, upload it to your site, and you can show them what's for sale on your site. In order to get there, we need to cover some of the theory first. We will start with vectors. So what is a vector? If we display it in two-dimensional space, then we can say that it's just two coordinates. In that case, it's a point. Or we can also display it as an arrow from the origin to that coordinates. We can also do the same thing for three-dimensional space. In that case, now we have a point or an arrow in three-dimensional space. If we want to imagine how it looks like in higher dimensions, it gets a little more complicated, right? Because we're used to 2 dimensions and 3 dimensions. In n-dimensional space, we can say it's just a set of numbers. So basically, that's a vector. Now, if we want to see how similar two vectors are, there are several possibilities how we can do that. One of them is cosine similarity. And the idea of cosine similarity is that two vectors are basically an arrow pointing towards a direction. And we measure the angle between these two arrows, between these two lines, so to say. And then if they are pointing in the same direction, we can say that they are similar or almost identical in that case. If they point in different directions, then they are dissimilar. So cosine similarity is one way how we can measure similarity between vectors. Also, that's just for visualization in two-dimensional space. The same method works in n-dimensional space with, let's say, 500 dimensions. Then another thing that we could use is the L2 normalization or Euclidean distance. What that does is it measures the distance between 2 points on a coordinate system. So here for visualization, again, we just show it on two-dimensional space. We have 2 points, and instead of the angle, we take the differences between the coordinates, and then that calculates the distance between these 2 points. So if we compare these two methods to see how similar vectors are, we can see that with cosine similarity, we measure the angle. With the other one, we measure the distance. And here's an important thing to notice. If we have two vectors which point in the same direction but have different length, then cosine similarity doesn't really record that, right? So for example, points A and E have the same distance with cosine similarity as the points A and B. But if we use Euclidean distance, then it becomes obvious that we get different values. So which one to choose requires some experimentation in the end, and also depends on the data that you capture on the type, like the vectors that you store in the end. So that's the rough theory for vectors, so we get a basic understanding just with geometric space, how that looks like and how we can measure similarity between them. Now, what we need to build our image search engine for our e-commerce system is some kind of image vectorizer. If we feed it an image of a painting, we want some vector as an output, because that's a requirement in order to index it in Elasticsearch. Now, there are several ways how we can do that. How can we transform a matrix, like an image, into a vector? For now, we can just assume it's a black box. There can be multiple ways to do it. And that's basically output. So now when we take all of our paintings in our web shop and we run it through that image vectorizer, we get one vector representation that captures the content of the image somehow. And we can index that in Elasticsearch. And now we can measure the distance from one image to the other one. The process of transforming a matrix like an image into a vector is usually called feature extraction. That's a term used frequently in machine learning as well. And the goal is to convert raw data with potential many dimensions, for example, pixels in an image. Every pixel would be one data point, into features with less dimensions, let's say a vector with 512 dimensions. And potential ways to do that are, for example, training a convolutional neural network for a classification problem. So we could, for example, use a network that is trained to classify the genre, or maybe the year from which the painting is. And with that trained classifier, we can extract intermediate data points from that network. And that way we can get a vector representation that captures part of the original image and part of the class that is to be classified. We'll see how that works later. Another way which works quite well is using autoencoders. An autoencoder has the task of receiving an input and providing as an output the same thing. So an autoencoder for an image, for example, takes as an input a handwritten digit. It somehow compresses it through a bottleneck, and then it tries to restore the original image from that compressed format to the same image, the hand-drawn image. Such an autoencoder is pretty good at compressing data, and in the middle of that autoencoder, we can also extract that compressed data in the form of a vector. So that's also one way how we could get vector representations from images or any other data set. Then there are multiple other algorithmic ways how we can do that, for example, with principal component analysis. If we had an input data set with many features, with principal component analysis, we would try to find features which are highly correlated, so we can collapse them into one. And let's say we get as an input like 1 million dimensions, and we use principal component analysis to compress that to maybe 500 dimensions. And then we have a compressed format that we can index again. The thing that I used for the demo that I'm going to show today was a convolutional neural network. It was trained to classify the style and the genre of a painting. The way such a network works is that we get an input, and that input is just represented as a matrix. So every pixel in an image is basically one data point in that matrix, and it gets passed through several layers of that convolutional network. So in the first layer, for example, we have several filters which are applied in windows going over all the pixels of the image. And for example, the first layer could do something like edge detection. And as an output in the pooled feature maps, they are kind of compressed to make them smaller. We get representations of edges from the image. So some data is lost of the original image, but therefore we get features like edges. In higher level feature maps, we have data points that represent higher level features, such as eyes in an image, or maybe a face. And in the end of that network, we run through another layer, which is not convolutional anymore, in order to flatten the data also to a vector representation. So now in this layer here, we would have a vector representation again, and we could extract that representation from the network with every image that we run through it. The last layer is usually the output for the classes. So if we have 5 classes, then here's a representation which class was identified with the classifier. That's how a convolutional filter looks like. Here in the middle is a filter, and it is applied in windows over the input image. And then we get outputs with different numbers. Very quickly have a look at an example of such a network. So what we see here is the different layers of the neural network. And the largest one at the bottom is the input layer. So that's a hand-drawn digit 3. And we can see in the first filters that were applied result in different images. But we can still recognize that it's a 3. We see that here there were some edge detections. So some vertical edges or horizontal edges or other edges are kind of highlighted because the filters computed a higher number for these fields. If we look into the later layers, it's kind of hard to recognize what the input originally was. That's because the further down we go in this network, the more abstract the representation gets. And depending on which layer we use to extract the vector, we get different results when we compare them or measure the distance. In the end, in this network, we flatten these matrices again to a vector, and here we already see like a one vector representation. Now that one's not two-dimensional anymore. Now we could go on and extract that vector for the digit that we do. And if we do the same thing for another digit, then some of these pixels change. And that's how we can see that the representation that's captured by the network also changes depending on what we draw. And if we take that extracted vector, we can compute the similarity between the representation in our network. So as we also saw in the interactive thing, the first layers do stuff like edge detection, and then higher level filters recognize things like eyes, for example, in complex image processing tasks. So if we put all these building blocks together, we can come up with a system that combines that. That's the components that I use to build a little gallery. So we have an image vectorizer, which is a trained neural network that I use to extract vector representations from paintings. Then I store the metadata of the images and also the vector representations in Kafka. And with a sink that is configured, that's dumped into Elasticsearch, into the Elasticsearch index. And now I have a gallery app, just a really simple Angular and Spring Boot app that acts as a client and runs queries in Elasticsearch to see similar images for a given image. So now that's the demo of the little application that I built for this talk. We have just a random sample of paintings that were indexed. We can use, for example, this one. And now we have different options to search similar images. I extracted vectors in different layers of the neural network to see how the results look like. What we see now is the fourth layer of the network. So the feature that was extracted is still very similar to the input image. And we can see that in the results. So the image up here is the search image. And what we get down here are the results by computing Euclidean distance of the vectors. We can see that the neural network learned basic features like the style of drawing. Was it a pencil? Was it some other way to paint that image? And it also learned the color representation. So here all images are black and white and have a similar drawing style. Now if we use a higher level feature, like a layer that was very close to the end of the neural network, where we have the classification for style, we get quite different results. Because here, the representation that was captured by the network is far away from the input image, but closer to the classification, to the class that was detected. Same as for genre, because genre is a different classification problem, and thus the representation is also different. And here we can search for other things. If we open a religious painting, for example, then we see that the results also show religious symbols, because the network learned these symbols and knows that they kind of belong to religious paintings. But the painting style can be quite different in the end. It can also be black and white and so on. If we go back to similar features, which was one of the early layers, we mainly get images that are drawn in a similar style with similar colors. Maybe we can see if there's also some abstract painting. This one, for example. Here we see that for some images it works very well to get similar images. But then if we use genre as a search criteria, it can be slightly off. But in the end, that's what we need to experiment with if we want to do a similarity search by complex features or attributes. It's basically what the model learns and how data is represented. What we need to do that is, of course, an index mapping. Here's the snippet that's responsible for storing the vector fields. In my case, I used genre and style vectors, and also a vector called common that was one of the early input layers of my neural network. I ran all images through my classifier, extracted the vectors, and then stored them in the index. Now, when we want to query for similar images, what we need to do is we submit a script query, and we use the script for scoring. And there are pre-built functions in PainlessScript. For example, cosine similarity is already implemented in PainlessScript. And we can pass the query vector that we sent in our query, and also the vector field of the document that is indexed. In the end, we just add 1 because the result could be negative and we don't want negative results. What we do here also is we have a match expression to just pre-filter for landscape genre. We can do the same thing for Euclidean distance. There's also a pre-built function that we can use. That would be L2 norm, and then the parameters are basically the same that we can pass in here. We need the query vector and the vector field of the document that has been indexed. You don't need to memorize everything. These examples are also in the reference documentation. Then for query time, what I did on this laptop while Docker Compose was running with Kafka and everything else, so the machine was quite occupied. But anyway, the median query time for these kind of searches was about 200 milliseconds on my machine. It's good to mention that Elasticsearch was just running on a single node for the demo setup in a Docker container. And I indexed 75,000 documents, so 75,000 paintings are in my index. And for testing, I ran the query over all documents, so I didn't filter previously. And that's also for that's vector field that stores 1024 dimensions. So query time is all right, but please keep in mind that this is still an expensive query because we need to calculate that score for every single document that we run in the query. So the recommendation is to run with filtering combined. You wouldn't want to run such a scoring query over millions of documents. That would be quite expensive. So the limitations right now for this approach is that the script needs to be run on every document because we use it for scoring. And thus it's recommended to combine that with filtering. So if we have a chance, we want to pre-filter our collection, so it's a reasonable amount of documents, and then we can apply the scoring. Also, vector fields are still considered experimental according to the documentation, but I think there will be some improvements ahead. There's still some activity on GitHub, and I think we will see further improvements in regards to vector fields. Right now, the dimension limitation for vector fields is 1024. That's starting from Elasticsearch 7.2. Previously, it was 512, I think. And also, if you want to use these vector functions like cosine similarity or L2 norm, then you should use Elasticsearch 7.2, and for Euclidean, I think it's a higher version. But you can see that in the documentation as well, when which function was added. So if we had like a huge collection, what we could do to further optimize that thing is that we, of course, combine it with filters. That's one point. For example, for images, we could have a histogram of colors and just pre-filter by color, for example, which would be one way to reduce the document set. Another way would be to use vector dimensionality reduction. There are some algorithms that we can use to reduce the number of dimensions in a vector without losing too much information. One of them is, for example, TSNE, which works quite well. Another one would be principal component analysis. And using that, we could reduce the dimensions from, let's say, 1024 to maybe 256, and that would already reduce the complexity of the computation and also the storage demand. The source code for the project is online on GitHub. There's a repository, image similarity search. We will probably share all these resources and the slides after the meetup, so you can check that out afterwards yourself. There's also an interesting article on Elastic blog for sentence embeddings, where they basically implemented search for short text snippets, where they capture the semantic meaning of the sentence. The same thing can be done with word embeddings, where the vector for a word basically represents the semantic meaning of a word. And there's also a link to the reference documentation, so you can see how the functions work. So that was a quick introduction to show how we can exploit the fact that now we have the possibility to index vector fields as well. It's just a little preview, and I think if you think about the domain where you work, you can easily come up with an example where it could be beneficial to have something like that. I used images because it's easy to show, but in the end we can also capture in a vector, for example, an insurance claim or maybe a portfolio or whatever you can imagine. If we can run it as a classification problem, we can also extract dense vector representations, and thus we can search in it. So there might be lots of areas where this comes in handy. Would be interested to hear what you think about it if you already have an idea where it could be used. Otherwise, we are open for questions to that demo. Thank you.